In the previous video, we talked about the integral definition of the natural log. And if you recall, what we said was that the natural log of a number, x greater than 0, is given by the definite integral from 1 to x of 1 over t dt. That is, the natural log of x is given by the net area under the curve 1 over t between t equals 1 and t equals x. Now we're going to build off that idea a little bit in this video to get to a new concept. I want to ask myself the following question. Is there a number b such that the natural log of x equals log base b of x? Or in other words, what is the base of the natural log? Another way I might state this question is as follows. Is there some b such that the natural log of b equals 1? So for the second question to make sense, we just need to remember the property that the log base b of b equals 1. Or for example, like the log base 10 of 10 equals 1. So essentially what I'm doing is I'm looking to find the base of the natural log. And you might already know what it is. Someone's probably told you in the past, but in this video we're going to see why. So let's concentrate then on finding a b such that the natural log of b equals 1. Okay, so the definition of the natural log is up here, right? The natural log of x equals this definite integral. So if I plug in b there, I'm going to get the natural log of b equals the integral from 1 to b of 1 over t dt, and I'm wanting that to equal 1. So then what I could write is that I want to solve 1 equals the integral from 1 to b of 1 over t dt. Well, first of all, let's ask the question, can we even know that there's a solution? And the answer is yes. We actually can know this, and let me tell you why. Let's take a look at our graph. So note first of all that the natural log is continuous on its domain. We've already examined that in the previous slides in this lesson. So next, I'm going to propose that the natural log of 2, which is the integral from 1 to 2 of 1 over t dt, is less than 1. So this natural log of 2 then would be the area under this curve between t equals 1 and t equals 2. And I'm not going to show this in detail, but if I were to approximate this using rectangles, I could clearly show you that it indeed was less than 1. Now further, I could show you that the natural log of 3, which is the integral from 1 to 3 of 1 over t dt, is greater than 1. Once again, I could approximate this using rectangles and prove to you that this was true, that this net area was greater than 1. So then based on those facts, and based once again on the fact that the natural log of x is continuous, I can conclude the following. By the intermediate value theorem, there must be some b between 2 and 3 such that the natural log of b, which once again is the net area under this curve, equals exactly 1. So we know that the base we're looking for is somewhere between 2 and 3. So by this we don't know exactly what the solution is. We don't know what our base b is yet, but we do know that it exists and that it's between 2 and 3. So now let's go a bit further and find out a little more information about this mysterious base b. So note the following. Let's say I want to take the derivative of the natural log of x and evaluate that at x equals 1. Well, we've learned before that the derivative of the natural log of x is 1 over x. So if I evaluate that at x equals 1, I'm going to get 1. Okay, so that doesn't seem particularly interesting yet, but let's try to write this in a different way. Okay, so I'm once again once again, going to look at the derivative of the natural log of x evaluated x equals 1. But this time I'm actually going to use the limit definition of the derivative. Okay, so if I do that, I can say that this equals the limit as h goes to 0 of the natural log of 1 plus h minus the natural log of 1 all over h. But we know from our previous work that the natural log of 1 is 0. So then this becomes the limit as h goes to 0 of the natural log of 1 plus h over h. And now we can use the properties of the natural log that we've learned to take this factor of 1 over h and make it an exponent. So now I can write this as the limit as h goes to 0 of the natural log of the quantity 1 plus h to the 1 over h power. Now one more little trick. Because the natural log is a continuous function, I can actually rearrange the limit and the natural log, and I can write this as the natural log of the limit as h goes to 0 of 1 plus h to the 1 over h power. And remember that we said before that this all equals 1, right? Up here we solved this a different way and we found that it equals 1. So what does this tell us? Well, remember what we're looking for. We're looking for a number, b, such that the natural log of b equals 1. Well, then this expression here must be our b, our base. So the base of the natural log is this limit. The limit as h goes to 0 of 1 plus h to the 1 over h power. And if you were to find a value for this limit, you would find that it's an irrational number. All right, that means a number that just goes on forever and ever and ever. So I can give you a few digits of it here: 2.7182818, and so on. It just keeps going forever. And we call this number e. So the base of our natural log is this limit, which is the number e.